see about Banker's algorithm and the resource allocation graph. Okay, so let us see what is Banker's algorithm, and this application is comes under which deadlock handling strategies. Banker's algorithm is a deadlock avoidance strategy. So as we saw in the previous video of deadlock, mm, deadlock avoidance is one of the strategy to avoid the deadlock. So by which application, which algorithm we are going to use for avoiding a deadlock? Banker's algorithm. So what is the logic? What is the steps? What is the procedure we are going to see for avoiding a deadlock? Okay. So it is called, why it is called as Banker's algorithm? Because it is used in banking system to decide whether a loan can be granted or not. The same way, when the process requests for a resources, whether it is safe to allocate the resources to the process or not. So the same strategy is applied in process allocation. That is the bank algorithm strategies is used in the process allocation approach, so that it is named as Banker's algorithm, the concept which is used in the OAS, so it becomes Banker's algorithm. Okay, so what are the data structures used in this Banker's algorithm? For implementing this Banker's algorithm, we use 4 data structures. One is available, and then max, allocation, and the last data structure is need. Let us see about let us see in detail about each data structures. First one is available. So it is a single dimensional array that specifies the number of instance of each resource type currently available. So it is a single array, single dimensional array. Say you can see here available of R1 is equals to K. So K in the sense the instance of resource type. As we see in the previous class, we have tape drive, right? So we have tape drive is common. We have many number of tape drives. So that is called as K instance. K instance of resource type of R1 are currently available. Okay, what are all the resources of same type currently available is what we called as available of R1 is equals to K in the sense number of instances. Say if the tape drive is 10, then the 10 is assigned to the availability. The second data structure, max. So it is a 2-dimensional array that specifies maximum number of instances of each resource type that a process can request. So every process may demand the resources for each process. So that is represented with the help of max of P1 of R1 is equals to K. P1 is nothing but what is the process type, and R1 is what is the resource type, and K is nothing but how many number of instance that requested by the process. Okay, maximum how many resources the process wants. Okay, and so here it means process P1 is allocated to ask for maximum of K instance of resource type R1. Okay. The next one is allocation. It is a 2-dimensional array that specifies the number of instances of each resource type that has been allocated to the process. Okay, currently how many number of, see we have 10 resources are there. So among 10, how many we can able to allocate so that the system will be in the safe state. So it is represented with the help of 2-dimensional array. Allocation of P1 of R1 is equals to K. It means K instance of resources type R1 have been allocated to the process P1. And the last data structure is need. It is a 2-dimensional array that specifies the number of instance of each process request for execution. Like currently, how many number of instances a process needs? A process may need a 10 resource type, 10 resources, but currently it may not require 10 resource type. Okay, it may require 5. Later sometime it may require other 5. Okay, currently the process requires how many number of instances. The current need is what we called as need data structure. So that is represented with the help of need of P1 of R1 is equals to K. So it means process P1 requires K more instance of resource type R1 for current execution. Okay, let us see how this Banker's algorithm works. So Banker's algorithm is executed whenever any process puts forward the request for allocating the resources. Okay, so it involves various steps. So let us see the steps and we'll move on to the problems. Step 1, Banker's algorithm checks whether the request made by the process is valid or not. The first thing is, so always it whether whether the request made by the process is valid or not. If the request is invalid, it aborts the request. Say for example, if the available resources may be 10, but a process may request more than 10, so we cannot allocate that. Okay, so the request is valid and it aborts the request. And if the request is valid, it follows the steps too. So once the request is valid, then it will move to the step 2. So what is that valid request? A request is considered valid if and only if the number of requested instance of each resource type is less than the need declared by the process in the beginning. So in the beginning itself, the process may require some resources. So that should be less than the availability. So that is what we call as valid request. So the availability must be the requested need must be less than the availability. Then the request must be valid, otherwise the request is not valid. Okay. So the next step is Banker's algorithm checks if the number of requested instance of each resource type is less than the number of available instance of each type. If the sufficient number of instances are not available, it asks for the process to wait longer. Say for example, I'm requesting for 10, but availability is only 5. Okay, maybe that requested resources held by some other process. So it will inform the process to wait for some time until the other process will release the resources. So if the sufficient number of instances are available, it follows next step. Okay, so the first step is it will check the request. If the request is valid, then it will be check whether the requested resources are available. If the resources are available, then it will move to the step 3. So what is step 3? Banker's algorithm makes an assumption that the requested resources have been allocated to the process. Then it modifies its data structure accordingly and move from one state to other state. Okay, so here as you can see, available is equals to available minus request of I. Okay, so it modifies the data structures accordingly and moves from one side to other side. Say if the available is equals to, just note down this for small formula for calculating availability, allocation and need. So available is equals to available minus request, allocation is equals to allocation plus request, need is equals to need minus request. Now Banker's algorithm. Now Banker's algorithm follows the safety algorithm to check whether the resulting state it has entered in a safe state or not. Okay, so how to check the state is how to check the state is safe state or not. If it is a safe state, then it allocates the requested resources to the process in an actual. Okay, if it is an unsafe state, then it rollbacks to its previous state and asks the process to wait longer. Okay, so see when the process may have a demand of requesting resources. Okay, whether you have properly allocated to the requested process or not. So when you allocate resources to the process, whether the system is in safe state or it may enter into a deadlock. So that is more important. Okay, so what is safe state? System is said to be in safe state when all the process can be executed in some arbitrary sequence with the available number of resources. Okay, so in order to check the system is in safe state or not, we use two data structure again. So to implement safety algorithm, following data structures are used. Data structures. are work and finish. These are all the two more additional data structures that ensures the system is in safe state or not. Okay. Safety algorithm data structures. So what does work and finish data structure means? Work. It is a single dimensional array that specifies the number of instances of each resource type which is currently available. Okay, so that specifies number of instance of each resource type which is currently available. So this is the representation of work data structure. Work of R1 is equals to K. It means K instance of resource type R1 are currently available. Finish is in single dimensional array that specifies when the process has finished its execution or not. So finish of P1 is equals to 0. It means process P1 is still left to execute. Okay. So let's see safety algorithm. So for safety algorithm, we require two data structures, work and finish. So safety algorithm is used to check whether the resultant state after allocating the resources is safe or not. So for that, the first step is initially the number of instance of each resource type currently available is equals to available of all process are to be executed. Okay. So in the step one, the data structures are initialized as work is equals to available. That is available is assigned to work, and finish of I is equals to false because no process is initiated. If no process is initiated, then the false state is assigned to finish of I. So for I is equals to 0, 1 to n process. The next step is so available is assigned to work, and initially no process has been allocated to the resources. Okay, and the second step is safety algorithm looks for an unfinished process who need is less than or equal to work. It will look for the unfinished process, and if that process really need an resources, and it will check whether that process need should be less than the availability. So if it is, then it will check the second process. It will check the second process based upon the index. Say for example, finish of I, initially I is equal to 0. It means a process 0 is false. It means it is not yet allocated. So it will check the need of first process should be less than work. If a such process exists, then step 3 is followed, otherwise step 5 is followed. See, it will check for all the process. Okay, first this is common for all the process. Say we have 5 process, it checks all the 5 process. If the first process is equals to false, it means unfinished process, and it checks the need, whether the need should be less than availability. If it is availability, then it will take to step 3, and if it is not, it will move to the last step. Okay, so assume now the need is less than is equals to work is nothing but availability. Okay, what is step 3? After finding the required process, the safety algorithm assumes that the requested resources are allocated to the process. The process run, finish its execution, and the resources allocated to it gets free. So the resources are then added to the work and finish it of I. That process is set as true. Okay, so once the process has been released the resources, then it will be added to the work. Already work is equals to work plus allocation. So this allocation assume it is assigned to first process. After the process executes, it will be released right after using the resources. That resource count is added with availability. Now you'll get the new work. Okay, and it will set finish of I is equals to true. Okay, so what does it mean? It will finish the first process execution. The next step is, so the loop will be continued for all the process. It will be repeated for all the process, and if all the processes are set to true, then it comes to step 5. If all the processes can be executed in some sequence, then the system is said to be in safe state. If everything has been finished in some order, it is not that it should follow in the process order, it should be in a different order. So in other words, we can say if finish of I becomes true for all I, then the system is in safe state, otherwise not. If any one of the process is still in false condition, then the system is in not safe state. Okay, let's start. As we saw two algorithm, one is Banker's algorithm and other one is safety algorithm. So these two algorithm, which is used for avoiding a deadlock, and we have some data structures used in it for avoiding deadlock, as well as we have safety algorithm that will ensure whether the system is in safe state or not. It means that whether we have properly allocated the requested resources to all the process and all the process requested resource has been satisfied or not. If any one of the process is in false state, then we can declare it is an unsafe state. Okay, let us see the first problem. The first problem here is a single processor system has three resources type X, Y, and Z, which are shared by three processes. So there are three resource types X, comma, Y, comma, and Z. These three processes shared these three resources shared by three processes. There are 5 units of each resource type. X is equals to 5, Y is equals to 5, and Z is equals to 5. Consider the following scenario where the column allocate denotes the number of units of each resource type allocated to each process, and the column requested denotes the number of units of each resource type requested by a process in order to complete execution. So which of the process will finish last? So we have four answer P0, P1 and P2. None of the above since the system is in deadlock. So the question is we have three resources X, Y, Z and three process P0, P1, P2. The question is which process will finish it fast. Otherwise, whether it is in if it is in safe state only, you can able to decide whether P0, P1 and P2 any one of the process will come at last, right? If it is a not safe state, then you can choose go for the last one. Okay, let us solve this problem. First, let us have this table. Okay, so this table will give you complete demand of resources of each process. Okay, as we saw in the question, there are three resources X, Y, Z of three process P0, P1, and P2. So this is already allocated resources. Already some resources have been allocated to the process P0, P1, and P2. Assume one instance of resource X is allocated to P0, two instance of Y resources allocated to P0, and one instance of Z is allocated to P0. Okay, similarly, 2, 0, 1 of all these instances allocated to P1 already allocated, and for P2, 2, 2, 1 have been allocated to P2. Now, after some time, the P0, P1, P2 requested for additional resources 1, 0, 3. That is, it additionally requires one more instance of X, and additionally it requires three more instance of Z for P0. And here for P1, additionally it requires Y instance of 1 and Z of 2 instance. And for P2, X of 1 instance, Y of 2 instances. Okay. Now, so according to the question, there are three resources X, Y, Z, and these three have five units of instances each. So total allocation is equals to X, Y, Z is equals to 543. So how this 543 will come? You need to add it. Okay, see, they have initially told this much of these number of units are available, and as you can see the previous table, you can add it. So how many it is allocated for X 5, 1 plus 2 plus 2 5, and for Y 4, and for Z 3. So totally the resources allocated from 555 is 543. Hope it is clear. Okay, 5 is nothing but initially these much resource instance are available, and after that some of the instances allocated to the process P0, P1 and P2. After allocating it, now let's see what is the available of the resource instance X, Y, Z. So how we can calculate the availability? So we have a formula. Uh, already, that is initially total minus total allocation. So what is the total here? Total instance of resources 555 minus allocated is 543. So now the availability, the actual availability of XYZ is 0, 1 and 2. So based upon this, we need to allocate resources of P0, P1 and P2. Okay, step 1. With the instance available currently how many resources are available? 0, 1, 2. Okay. Available currently, only the requirement of the process P1 can be satisfied. Okay, let's go back to the box. Okay, what is the availability? The availability is 0, 1, 2. Current availability is 0, 1, 2. Now we can compare which process you can allocate with 0, 1, 2. 0, it is, you cannot allocate. See, 0, 1, 2 is the current availability. So X, but here the process P not requested for the additional resource 1, but we currently it is null. And Y it is not requested, and for Z it requires 2 more additionally. But here we have 3. Okay, current availability is 0, 1, 2, but here it requires 1, 0, 3. So we cannot satisfy P0 process. Let's check P1 process additional request 0, 1, 2. So here X instance is not required, Y instance is required, and Z instance is required. So yes, we have a current availability of 0, 1, 2. We can satisfy P1 process first. Okay. Yeah. So a process P1 is allocated the requested resources. So whatever resources that is requested by the process P1, that can be allocated. So it completes, once it completes its execution, then it will free up all the instance of resources held by it. So assume we have allocated and it is freed all the resources. So what is the availability already there? 0, 1, 2, and already allocated is 2, 0, 1. So already allocated is 201, and the requested resources can also be allocated. So if you add this both 012 plus 201, you can get the new availability. So what is the new availability? 213. 213 is a newly available resources. Now you need to check this current availability with the process request. What is the current availability? 213, right? Now, with the instance available currently, only the requirement of process P0 can be satisfied. So process P0 is allocated the requested resources and it completes the execution, then it free up the instances of resources held by it. So the current availability is already 213 plus the requested resources allocated to the P0 is 121. When you add, you will get 334. Okay, so now the current availability of the resource is 333. Okay, now with this availability, you need to check the remaining process. Already P0 is over, P1 is over. Now the next one is P2. So the instance available currently, the requirement of the process P2 can be satisfied. So the process P2 is allocated the requested resources and it completes execution. Then it free up the instances of resources held by it. So finally, the current availability is 334 plus 221 is the allocated resources for process P2. So when you add these two, you can get the current, you can get the availability which are already initially available of all the resource type X, Y, Z. So 555. So now you have carefully allocated resources of all three process, and which process ends at last? P2. Okay, now the system is in also safe state. So what will be the answer then? So what is the sequence, safe sequence that it follows for execution of allocating resources? P1, P2, P1, P0, P2, in which all the processes can be executed. So the system is in a safe state. So process P2 will be executed at last. So the correct answer is option C. Okay, let's see the second problem. So the second problem is an operating system uses a banker's algorithm for deadlock avoidance When managing the allocation of three resource types X, Y, and Z to three processes P0, P1, and P2, the table given below presents the current system state. Here the allocation matrix. So allocation matrix shows the current number of resources of each type allocated to each process, and the max matrix shows the maximum number of resources of each type required by each process during its execution. Okay, students, if you have any doubt, you can raise your hand and ask me at instantly. Hope you have understood how the system safely allocate the resources so that we can make sure the system is in safe state. You have any doubts in problem one? Shall we see the problem two? Okay, let us see the current state of problem two. So this is the current safe state of second problem, and this will show you the allocation and maximum demand of each process. So X, Y, Z are instances, and already allocated of resources are 0, 0, 1 to P0, 3 to 0 of P1, 2, 1, 1 of P2. So the maximum demand of each process are 8, 4, 3, 6, 2, 0, 3, 3, 3. So there are three units. There are three units of type X and two units of type Y and two units of type Z still available. The system is currently in safe state. Consider the following independent requests for additional resources in the current state. So the first request may be, okay, P0 requires 0 unit of X, 0 unit of Y, and 2 unit of Z. This is the first request. And second request, 2 unit of X, 0 unit of Y, and 0 unit of Z. So which of the following is true? Only request 1 can be permitted, only request 2 can be permitted, both requests can be permitted, neither request 1 nor request 2 can be permitted. So let us check by using the Banker's algorithm. Okay, first according to the question, the available is equals to X, Y, Z is equal to 3, 2, 3, 2, 2. Okay, 3, 2, 2. After allocating some resources of X, Y, Z, we have some balance of X, Y, Z. They are 3, 2, 2. So now we need to find out what is the need of each process. Okay, how we can calculate the need of each process, maximum minus allocation. So you know in this table we have maximum demand. So if and already allocated, if we subtract maximum minus allocation, then you will get the need of each process. Okay, so the need of each process is calculated by need is equal to maximum minus allocation. So currently the system is in safe state and it is given in the question. The question itself, they said that currently it is in safe state. Now we want to check if any process make a request, whether we can able to fulfill the request or not, whether still it is in safe state or unsafe state. Okay. So need of P0, P0 is equals to 0, 0, 2. When you subtract 8 minus 8, 4, 3 minus 0, 0, 1, you'll get so according to the question, available is equal to 332. So maximum minus allocation. Okay. So process P0 need is 0, 0, 2. So as you can see, this is allocation already allocated 0, 0, 3 and maximum is 843. 843 minus 0, 0, 3, you will get the need is 840. So the need of process 1. And the P1 already allocated is 320 and the maximum demand is 620. So what is the current need of P1? 6 minus 3, 3, 2 minus 2, 0, 0 minus 0, 0. And then similarly, 3, 3, 3 is the maximum need. For allocated is 2, 1, 1. The need of process P2 was 1, 2, 2. Okay. So, after allocation of the available resources are 3, 2, 2. With the instance available currently, the requirement of request 1 can be satisfied. Okay, so Banker's algorithm assumes the request R1 is entertained. Okay, because the additional request of R1 is additional request of R1 0 0 2 0 0 2 is the additional request. And since they said already the system is in safe state, if the additional request 002 can be satisfied or not. Yes, it is satisfied because the availability is 322. So it is then modifies its data structure as follows. So after allocating this, we will get what is 322 minus 002, you will get 320. Availability is now 320. And now it follows the safety algorithm to check whether this resulting state is in a safe state or not. If it is a safe state, then the request RQ1 can be permitted, otherwise not. Let's see the first step. So with the instance available currently, only the requirement of the process P1 can be satisfied. So the process P1 is allocated the requested resources. It completes its execution and then free up the instance of resource held by it. So then what is will be the available 320? Available is already 320. After process P0 it made use of the resources and it released, then you will get the resources as 320. Adding this, you will get 640. Okay, this is available and this is already allocated to P1 process. Okay, so it is not possible to entertain any process. The system has entered the see. If you got 640, then you cannot fulfill P0 process and P2 process. So it is not possible to entertain any process. So the system has a deadlock state, which is in an unsafe state. So that the request will not be permitted. The request one will not be permitted. Now, so now need of process one is 200. We are taking the P1 process now. Availability is 322. So clearly, with the instance available currently are the requirement of request can be satisfied. So Banker's algorithm assumes that the request 2 is entertained. It is then modifies the data structure as available is equals to 322 minus 200 and the current availability is 122. So now it allows the safety algorithm to check whether this resulting state is a safe state or not. If it is a safe state, then request 1 can be permitted, otherwise not. Okay, with the instance available currently, only the requirement of the process P1 can be satisfied. Process P1 is allocated the requested resources and its complete execution, then three of the instances of resources held by it. So then availability is equals to 122 plus 520, you will get 642. So now it follows the safety algorithm to check whether this resulting state is a safe state or not. If it is a safe state, then request 2 can be permitted, otherwise not. Okay, so with the instance available currently, only the requirement of the process P2 can be satisfied. So the process P2 is allocated the requested resources. It completes its execution, and whatever resources it is with that process, that will be PR. Then the available is equal to 642 plus 211853. So with the instance available currently, the requirement of the process P0 can be satisfied. So the process P0 is allocated the requested resources. After using the resources, it will be freed. So available is equals to 853 plus 001, which is equal to 854. Okay, thus there exists a safe sequence in the order P1, P2, P0, in which all the process can be executed. So the system is in safe state, so that the request can be permitted. So finally, the correct option is B. So let us see the next problem. A system has four processes and five allocatable resources. The current allocation and maximum needs are as follows. Okay. So the allocated, so how many processes are there? There are four processes, A, B, C, D, and allocated resources given, and maximum need is also given. So availability also they have given as 0, 0, cross 1, 1. What is the smallest value of X for which this is a safe state? So you need to find out the availability of the third instance. Okay, let us calculate the additional instance of each resource type needed by each process. So how to calculate the need of the remaining process? Need is equals to maximum minus. Okay. So when you do this, you will get A is equals to 0, 1, 0, 2. For process B, 0, 2, 1, 0, 0. And for process C, 1, 0, 3, 0, 0. And for process D, 0, 0, 1, 1, 0. So we have let us take case 1. For x is equal to 0, you need to assume the third instance initially x as 0, then availability is equal to 0, 0, 0, 1, 1. So you need to find out what will be the smallest number for that resource instant type, so that the system must be in the safe state. So with the instance available currently, the requirement of any process cannot be satisfied. So when you take x is equals to 0, the system remains in deadlock, which is not a safe state. Okay, now we are taking case 2 for x is equals to 1. If x is equals to 1, then the availability is equals to 0, 0, 1, 1, 1. So let us see the first step. With the instance available currently, only the requirement of the process B can be satisfied. So the process B is allocated the requested resources. It completes execution and then free up the instance of the resource available. Then what will be the availability? Availability of already allocated is 00111. Uh, 0011 is the current availability. Already allocated is 11110. So when you add it, you will finally get the availability 11221. The instance available currently, the requirement of any process cannot be satisfied. So for x is equals to 1, system remains in deadlock, which is in an unsafe state. Now we are taking case for x is equals to 2. We are taking x is equals to 2. Taking x is equals to 2, then available is 0, 0, 2, 1, 1. So with the instance available currently, only the requirement of the process B can be satisfied. So process B is allocated the requested resources. It completes execution and then free up the instance of resources held by it. Then the availability is 00211 plus already allocated as 11110. So finally the availability is 11321. Okay. So now second step. So we have taken different cases by choosing different values for x. So final minimum value we have taken for x is 2. So with that the system remains safe state. So now let's see step 2. We are ensuring whether the system isn't whether we can able to satisfy the C process request or not. With the instance available currently, only the requirement of the process C can be satisfied. So process C is allocated the requested resources. It completes its execution and then three of the instances of the resources held by it. Then available is equals to 11321 plus 11011, and finally when we sum up this we will get 22332. So there exists a safe sequence in which all the process can be satisfied. So with the instance available currently, the requirement of both process A and B can be satisfied. So process A and B are allocated the requested resources one by one, and they complete their execution, then free up the instance of the resources held by it. Then the available is equals to 22332 plus 10211 plus 20111 is equals to 52653. So thus there exists a safe sequence in which all the processes can be executed. So the system is in a safe state. So minimum value x that ensures the system is in safe state is equals to 2. Okay. Yes. So what we saw as of now is Banker's algorithm with the related problems, right? So now you are moving into the resource allocation graph. So resource allocation graph is a graph that represents the state of a system uh, pictorially. Okay, pictorially it represents whether the system is in safe state or not. So it is an graphical representation. We can say whether with that representation we can easily identify whether the system is in safe state or not. So what are the other information that is given by resource allocation graph? So it gives complete information about the state of a system, such as how many processes exist in the system. So visually you can see how many processes exist in the system, how many instances of each resource type exist, how many instances of each resource types are allocated, and how many instance of each resource type still available, how many instance of each resource type are held by each process, how many instance of each resource types are held by each process, how many instance of each resource type does each process need for execution. Okay, there are two major components of resource allocation graph. One is vertices and edges. Since it is a graphical representation, we have obviously we have vertices and edges. Let's see what does it vertices and edges means. The vertices we have types of what is this types of process vertices and resource vertices. Resource vertices are again further classified into single instance and multiple instance. Vertices. Vertices represents process and resources. Okay, process vertices represents the process. They are drawn as a the name of process inside the circle. Resource vertices represents the resources. It depends upon the number of instances that exist in the system. Resource vertices may be single instance or multiple instance, and they are drawn as a rectangle by mentioning the dots inside the rectangle. The number of dots inside the rectangle indicates the number of instances of that resources existing in the system. So let us see a pictorial representation. As you can see here, process. As you can see, process is represented with circle. and resources are represented with the rectangle, and this dotted represents how many number of instances being allocated uh, for the process. Okay. So now let's see edges. There are two types of edges in resource allocation graph. It just connects the resource with the process. The first one is assign edge. The next one is request edge. Assign edge represents the assignment of resources to the process. So they are drawn as an arrow where the head of the arrow points to the process and tail of the process points to the instance of the resources. Okay. Edges means it will requesting the request edge represents the waiting state of a processes for the resources. They are drawn as an arrow where the head of the arrow points to the instance of the resources and tail of the process points to the process. So if a process requires n instance of a resource type, then n assigns edges will be drawn. So here is an example of resource allocation graph. So as you can see, you can get various information from the resource allocation graph. So the first information, there exists three processes, P1, P2 and P3. And there are two resources, R1 and R2. And there exists only a single instance of R1 and two instances of R2. Process P1 holds R1 and P1 requesting for R2 instance. Process P2 requesting for R1 instance. P2 holds the R2 one of the instance and R2 instance is held by P3. So all this information you can easily get from this pictorial representation. Okay, deadlock deduction. So why we studied this resource allocation graph? So this resource allocation graph, which will be helpful for us to deduct the deadlock occurrence or deadlock situation in the system or not. Okay, in simply we can say using a resource allocation graph, it can be easily deducted whether the system is in a deadlock state or not. That is why we are going for that pictorial representation of resource allocation graph. So we have some rules to be followed uh, to deduct the deadlock situation. The first one is resource allocation graph where all the resources are single instance. If a cycle is being formed, then the system is in a deadlock state. If no cycle is being formed, then the system is not in a deadlock state. In rule 2, in resource allocation graph where all the resources are not single instance. If a cycle is being formed, then the system may be in a deadlock state. Banker algorithm is applied to confirm whether the system is in deadlock or not. If no cycle is being formed, then the system is not in a deadlock state. Presence of a cycle is necessary, but not a sufficient condition for the occurrence of a deadlock. Okay, so I think uh, the problems we will see in the next class, students. So far, you have any doubt? So what we have saw as of is Banker's algorithm, how we can avoid the deadlock by using Banker's algorithm and safety algorithm with some practice problems. And then we have other method called the resource allocation graph, and we saw the components of a resource allocation graph and how we, what are the rules of to be followed, and how we can easily deduct the deadlock in the resource allocation graph. So I think the concept is clear for you, and we will see in the next video, we will see various practices problem based upon this resource allocation graph and how we can easily deduct the deadlock. Easily deduct the deadlock. Thank you, students. You have any doubt, you can raise out. Students, you have any doubts, voice out. Okay, students, thank you. We will see more practices problem on next class. Thank you.